and you have, it becomes positive when you go over here. Divided by 5 times 10 to the minus 3. So now you just put that in and then take the square root of it. Tell me what you get. Six 6,706.3 meters per second. So that's pretty fast. Very fast. No, they're going very fast when they hit each other. Okay, part E now is how much work do I need to do to bring another charge from from infinity all the way to the origin. Okay, so I have the original system is negative 3, 0. So another charge is coming here. What was that other third charge? Negative 0.4. Negative 0.4 millicoulombs. Okay. So I'm going to bring that charge from infinity to that point. Now, so now assume that these two are fixed again. So don't assume that they're coming together. Assume these two are fixed. This thing is coming to the origin, which is somewhere here, right? It's closer to that one. Do you think this thing wants to come to the origin by itself, or are we going to have to force it? Okay. It depends what the potential is, right? The potential at infinity is 0. What's the potential at that point? Have we found the potential at origin? I don't think we did, right? So let's 9 times 10 to the 9th. I believe it's going to be negative, right? 9 times 10 because it's closer to that. So 5 times 10 to the minus 4, negative 5 times 10 to the minus 4 over 3, plus 2 times 10 to the minus 4 over 4. Since it's closer to that guy, the negative is going to win. So the potential is 9 times 10 to the 5th, negative 5 over 3, plus 1 over 2. Negative 10 plus 3 over 6. Negative 7 over 6. So what is that? Negative 63 over 6 times 10 to the 5th. So do that. Tell me what you get. Yeah, it should be. Negative 10 plus 3 is 7. The 6th. And it's negative, right? Okay, so the potential at infinity is 0. The potential at that point is negative. And this charge is negative. So do the negative charges like to go towards a lower potential or higher? 0 is higher than this. So this is negative. Negative charges like to go towards higher or lower potential? Higher potential. Positive charges like to go towards lower. Remember it this way. Positive charge is like equivalent to any mass on Earth. Okay? Masses like to go towards lower potential. Negative charges is if there was any object that had negative mass, which we don't have. If you let go of it, it would go up. So negative charges like to go towards a higher potential. So since 0 is higher than negative, negative charge likes to go this way. So it doesn't want to go there. So I suspect that when we get the answer, we're going to get a positive answer. I'm going to have to do positive work. I'm going to have to do positive work to bring it here. So here's there's two ways that you could get this answer. You can either say the work that I'm going to have to do is equal to the potential, the Q delta V, absolute value. So I'm going to have to do positive work to make it go there. So I'm going to do absolute value of Q delta V. So I have its charge is equal to 0.4 times 10 to the minus 3. And delta V is the potential at that point minus the potential at infinity, which is 0. So it's the potential difference between the two. Minus 0. Then we're taking the absolute value of that. So in other words, since I knew that it's 0, I'm just going to take the absolute value of whatever potential it's going to have there. Since the infinity the potential is 0, so I'm just taking that potential times its charge. So then it's going to be 4 times 10 to the minus 4. So this is going to be 4 and then this is 4.2 times 10 to the second, right? So 420 joules. That's it. That's the answer. So I'm going to have to do 420 joules of work to make it come there at a constant velocity. Now, if I want to accelerate it, so I'm actually going to push it here. If I want to actually accelerate it, and if I want it to have a certain velocity here, then I'm going to have to do even more work, right? Which means you would have to add to this the whatever kinetic energy you want it to have at that point. You would have to add to it half mv final squared, right? So you're going to have to do a minimum of 420 joules just to make sure it goes there at constant velocity. But if you wanted to accelerate, you'd add to it the kinetic energy. The other way of thinking of this problem is this. Think about this charge as already present there. This is a different approach to it. Think about this three-charge system and ask yourself, what is the potential energy of this three-charge system? You see? It's the same, we're going to get the same answer, but it's a different way of looking at the problem. What's the potential energy of this three-charge system? Well, these two have a potential energy. And then this is your third charge, right? So these two have potential energy, K, Q1, Q over this distance, D1. And then these two have potential energy. Okay, so what I want to do, what I'm solving for is the potential energy of this that it has with respect to those two, because of those two. Okay, that's the potential energy of this charge, the little q. I'm not solving for the potential energy that these two have, the two outer ones, because I don't care about splitting those. you see. So those two assume they're fixed.